All right, we're going to get started with day 6. Elijah Flenner, who's I don't know what your official position is, this research scientist, in the department here. He works on glassy dynamics and MD simulations thereof. So,
how's it autoplaying?
So he'll be teaching class today, and today we're moving on. So yesterday you guys covered how to compute energies in a classical force field, and today we're going to move on and talk about dynamics and computing properties from an MD simulation, and then moving towards more complex systems over the last few days of the class. So,
all right. Thank you, Mike. So, as I understand, you've you talked about energies in classical force fields. So you're talking a lot about, when you have, say, a molecule or a couple molecules interacting with each other. So a lot of, which, very interesting, if you have one benzene, we're doing a lot of examples with benzene here. You have one benzene, a benzene dimer that's interacting. Those are interesting, but a lot of the problems we have is we have more than one molecule. We have a mole of them, or we just have a lot. And there are different properties emerges when you have all these different molecules. Now, specifically, I do a lot of simulations of liquids, and we'll be looking at simulating benzene liquid today. So, what really is classical molecular dynamics simulation? It's really a numerical method, and a lot of the simulations are based on Newton's equations of motion, although there are other things you can do. But we are interested in calculating thermodynamic quantities. Things like, for liquids, maybe a specific heat, might be interested in compressibility. Martin does a lot of free energy calculations, so free energy differences between different states, different states of matter to know which one's the most probable one in a given condition. I use these simulations a lot to test fundamental theories of the class transition. But it really provides a means where we can create these force fields that you talked about, these potential energy functions, and connect the microscopic behavior of the atoms to experimental results. So the basics are that for most molecular dynamics simulations, you can do, they call them ab initio simulations and start from first principles, but those are very slow. So most simulations, what one does is create force fields, and that's what they're talking, as I understood, talking about creating these potentials. And there's many different potentials or parts of the potentials, but a lot of times they have bonded interactions. These bonded interactions will have different torsionals and rotations, have non-bonded interactions. Sometimes they have 3-particle interactions. But after the molecular dynamics simulations aren't interested in the creation of the force fields, but some of the Tony's work and stuff can help create these force fields. And then what the force fields are, then you can calculate the force on a particle. So I guess I can point here. So this F of n is a force on particle n, and it equals the negative gradient of the potential. Now this looks a little, I don't know how much you've seen of this, but it's in essence a fairly simple idea that's easy to code in the simulations. So you have one equation for each particle, and for each direction of motion, the x, y, or z direction. And the potentials, like I said, have bonds, interactions, torsions. And when the potential is a minimum, since the force is the derivative, then the force is zero. And then the simplest molecular dynamics simulations are how this started. We used Newton's law, F equals ma, to determine the accelerations. We use accelerations to update the velocities. And then you use the velocities to update the positions. And when you get a new position, you calculate new forces, and you continue with this process. There are very many different numerical methods to do this. That's beyond the scope of this lecture, but and then once you go through this, well, you have a whole series in time of where the particle positions are of your many particle system, and then you can calculate quantities of interest using statistical mechanics to calculate what you need. And I think of this as kind of a numerical experiment a lot of times. You have some of the same sort of things that are happening in experiments. When you start it, you don't really know what the outcome is going to be. You always have to worry about the errors in the calculations, the uncertainties, and everything. Anyhow, so that's the very basics. Now, to set up a simulation, what do you need? First, you need some sort of initial conditions, the initial positions of your molecules. Now, if you think about this, if you have a liquid, say, let's take our benzene that we've been thinking about. And so that thing is a ring, in some sense. And we need an initial position that is consistent with the thermodynamic conditions we're interested in. So this is not just throwing a bunch of benzene rings into some sort of simulation container and running a simulation. We need to first create a bunch of benzene rings at the proper initial conditions. We can't just put them in randomly because they'll have overlaps. We got to somehow create this. So, and these complicated systems can require care of how to set up the simulations and run the simulations. Another part of it is we need some initial velocities. Unfortunately, this is a fairly easy thing to do. We can just choose it from a Boltzmann distribution, which is given here. The positions and velocities are uncorrelated, so you don't have to worry about that. You can just, every velocity you can choose at random from a Boltzmann distribution. Also, fortunately, in simulations, the velocities quickly become a Boltzmann distributed during the run of the simulation anyhow. So what's important though is that there's a temperature in the Boltzmann distribution. So that's what this T is. This is the Boltzmann constant. And so you need to choose your velocities consistent with this temperature. So for whatever you want to simulate, whatever conditions you're interested in, needs to be consistent with that temperature. And I'll talk about the temperature in a little bit. So first you have a bunch of particles in a box, say a bunch of benzenes in a box. And a lot of times to put them in there, there's programs to hydrate, to put water around molecules and everything. And those waters will be not necessarily oriented correctly. And so there may be atoms that are closer than you really want to be. And then the forces may be very large. And you just start a simulation, but it ends up is the thing just essentially blows up. Particles go everywhere. So what is typically done is after you emit, and a lot of these biological ones, I mean, you can either start smartly, you can start by putting everything on a lattice, but that can take a while to melt, take a while to start things. A lot of times what we do is we just minimize the energy. So this, what it does is sets all the initial forces to 0. And this way, there's no large forces, or around 0. There's no large forces, and then the system doesn't blow up. But you still have velocities for whatever temperature you're interested in. So you give them initial velocities, and this is a typical way to start the simulations so that that we can so that they run without any dramatic effects. But since you're starting it at an energy minimum, it's not at a typical energy given the conditions that you're interested in. So after you minimize it, the energy, we have to equilibrate the system to desired temperatures and pressures. You don't know the volume of the box, the density, essentially, of the system for a given thermodynamic condition all the time. So we want to equilibrate it to the desired temperature and pressure. I'll describe a little bit how that's done, but there's many different ways to do all this. Temperature equilibration, mostly done with a lot of times done with a thermostat, what we call a thermostat. Many different numerical algorithms that can equilibrate it to a specific temperature. The simplest one is actually, remember, the velocity distribution. There's a temperature in there. The simplest one is every so many steps, rescale the velocities to be consistent with the temperature. Later on, I will briefly describe what's called a Langevin thermostat, the different way that they do it, give you an idea of how that is. It generally works a little bit better, but and then the pressure equilibration we do with a barostat. Once again, many different ways to do that. Future example, I'm going to show you how to implement a Monte Carlo, what they call a Monte Carlo barostat. And then after you have equilibrated it, then you can run your production runs and calculate the averages. Now these production runs, exactly how you run it is depend on what you want to calculate. This, in my mind, is a very important thing to keep in mind in dynamic simulation. Is that you really want to design your simulations all the time around what you want to calculate, what you want to know. Not just run them blindly and get results, because different ways to perform the simulations will give you more accurate results for what you want to calculate. All right. So the other point is we also use what's called periodic boundary conditions to simulate large systems. we still can't simulate 10 to the 23rd particles. We can simulate quite a few. We get up to, I've done 8 million. But people will do a little bit more than that, like 8 million atoms. But you can't really do a macroscopic system. These things are still very microscopic. So to be able to get quantities that are similar to what is found in bulk systems, what we use what's periodic boundary conditions. We'll use benzene as an example throughout this lecture. I do have a slide somewhere with periodic boundary conditions. So, and you'll see what it is in our in these examples. All right. So hopefully you all downloaded the examples. Did you? No. They're what's that? Yeah, they're on the cluster. They're already up. So you can open DMD and take a look. Okay, so let's take a look at the minimalization. So in examples, min, right? This is the example of what it looks like when you run a minimalization. Hopefully this works here. Oh. So this one you want to load it without periodic box. There we go. So I did it from the command line. If you don't remember how to do that, you can just open BMD, go to Files and Molecule, and then just in the examples folder, load in the benzene PMR top, and before you close anything, before you close the load, then you can load in the min folder benz.min.mdcrd, this file. And it should look like this. So what I did here there we go, is I was given a bunch of benzenes, and Rex actually gave me this initial configuration. He created it, and I think he told me he put it on some sort of lattice, and I don't remember what it was. But when he gave this to me, there's overlapping atoms. So I just started with the molecular dynamics simulation. It doesn't work. So the first thing I do is minimize the structure. So when I did the minimalization, and I'll show you in a minute how we went about that. This is what the structure did. So you can see the benzenes are moving around to find the minimum position. All right. So I used Amber, the simulation package, to do the minimization. To tell you what's going on, you notice you load in two files. The first one is a parameter file. And that parameter file that you load into VMD is also used in Amber. And that contains the information about the force field, so the information about the potentials, and identifies what the atoms are in the coordinate file. It identifies all the benzenes. So, I'll show you the molecular dynamics script used to do that minimization. But this is the general structure of these scripts. There's several of them. Or this gets a little boring, but the first line is always a comment line. You can put anything there you want. A good idea is to put in there what the thing's going to do. The second line is ampersand control. And then you have a bunch of lines that describe the simulation that's going to be performed. In general, lines are a keyword equals some sort of number. The numbers may be integer flags or floating point numbers or something telling you something about the simulation, what the keyword. Between each command, there's a comma. Don't forget the commas. And there's many options. We'll only go through a few. And there's, of course, documentation of how it's done. So, in the min folder, there is this script that tells you that the benzene minimization. So we have the control, and I guess you can use the pointer. All right, and so the first line is just a flag that tells you that you're performing energy minimization. So 1 means you're performing minimization. That's true. 0 is false. But you're not performing an energy minimization. Then you have another flag telling it it's going to read in the coordinates and velocities. Or the flag telling you whether or not it's going to read in coordinates and velocities. 1 means it reads coordinates and no velocities. There are other ones where it's going to you can tell it you're going to read coordinates and velocities. But here, so it'll since we're doing energy minimization, we don't need any velocities. The IREST is a flag for a new simulation. And 0 means it's a new simulation. There's many ways to do energy minimizations. This one is we're doing what's called a steepest descent, which all it is, if you have a potential energy surface, these potential energy surfaces depend on the number of atoms to the 3n in your system, so they're very complicated, very huge, very hard to visualize. But steepest descent, all it does is it finds the steepest direction downward. And then it just follows that. And then I think it finishes with a conjugate gradient. So, so we have the max number of iterations. So if it doesn't find an energy minimization minimum after the max number of iterations, it'll stop. Then we have a flag for the we tell it how many times to print the output, which is NTPR. How many times we're saving the coordinates, the cutoff for the non-bonded interactions. So when you have a potential energy function for non-bonded particles, so bonds is easy because there's only the maximum length of the bond. You know, they kind of stay around each other. But you have all these particles, you have these non-bonded interactions. So this is, and as they get farther apart, the interaction is never zero. But you can't do the calculation for infinitely separated particles or particles after a certain distance. So we have a cutoff for these non-bonded interactions. So that's what cut means. And then there's there's different ways to save the output. So this is last one is a flag for the output file. All right. So now, after you have all that, that input file, to run it, and there's details on the website of how to run this on the cluster. But this is the command to run it. You can these will run on a GPU, or they'll run on the CPUs. So real quick, the -O is I'm telling it to overwrite any file that's there. Be careful with that. Because you don't sometimes, you don't want to lose data. But if you don't have the -O, it won't overwrite files. And if there's, it'll give you an error message if the file exists. So the -I, and what's after that is the input script. So that the bin, that in is just the input script I just showed you. There's a log file that's printed every so many steps. The parameter file, and that's what we loaded into VMD also. So that gives you the force field and the topology. You need an input coordinate file. And that's here too. I did not provide the input coordinate file in the examples, but you'll see how we can create those. Final restart file is an output coordinate file. So at the end, an output coordinate file, which is the coordinates while the simulation is running, and information about the simulation written every so many steps. All right, so we've already loaded in the trajectory and visualized what was going on and seen what happens during the minimalization. So the next thing, so after we minimize the energy, and this is, a lot of people think of this as a T=0 configuration. So technically speaking, if you're at 0 temperature and there's no velocities, everything should move towards a minimum energy configuration. So then we can heat it. Typical thing to do is heat it from its 0K to 298K. So I'm not going to go through things that we did before, but once again, reading coordinates and at velocities. I have a flag for the periodic boundary conditions. So when I did the memoization, I actually didn't have periodic boundary conditions there. Now I have a flag for the periodic boundary conditions. These are periodic and fixed. And that one means that. NTC is a flag for constrained bonds. And here we're going to constrain the hydrogen bonds. Now, why do we do that? Sometimes you do simulations where you allow all the bonds to fluctuate. Sometimes you constrain bonds. And some bonds, you just have them at a fixed length. And the reason that is done is because the simulations can be faster if the bonds aren't allowed to move. These bonding interactions are generally, the potentials are steep. And when you do these simulations, you have a time step, which is given here. And if you fix the bonds, the time steps can be bigger. However, this is obviously not as realistic to have fixed bond lengths. If you're interested in how the bonds are changing, you don't fix the bonds. Now, it is very common to fix hydrogen bond lengths. This allows you to have a bigger time step, and the hydrogens move fast enough that it's generally considered not a huge disadvantage. So here we're fixing the hydrogen bond lengths, but not any others. I'm also, and since I've fixed those, I don't have to calculate the hydrogen bond forces. Right, so those bonds are fixed, and so I'm going to tell it not to calculate the forces for the hydrogen bonds. This is not what you, like in water, you have hydrogen bonding. This is not what I'm talking about. This is the bonds of the hydrogens bonded to the molecule.
Covalent.
What's that?
It's the covalent bond.
Yes, it's the covalent bond. Let's see. So temp I is the initial temperature, and then I'm going to heat it up to the final temperature. And to do this, like I said, there's many different ways to do this. And here I give it a flag, the NTT, for Langevin dynamics. And I'll describe in a little bit what that does. Like I said before, you can do just velocity rescaling, scaling it to a certain temperature. There's also different thermostats that people use. For some reason, I chose the Langevin one this time. And so when you do that, you have to give it a gamma, which is a parameter for the temperature coupling. And then the NT, this is the number of simulation steps. ET is once again a time step. Then I print out to MD out and MD info every 100 steps, saving coordinates every 1,000 steps. And because of the thermostat uses using random numbers, So we give it a random number seed. So in simulations, in computers, you create random numbers by what's called a pseudo-random number generator. These aren't truly random. They depend on the number before it, but you start these random number generators with a seed. You start with the same seed, and you're running at one processor. The the numbers generated are always in the same order. You run on multiple processors because of speed conditions, it can be in different order. But, so when you test things, a lot of times you want to test it with a known seed so that everything's going along in the same order and you can figure things out more. If otherwise, it's kind of nice to have different seeds for different simulations. An easy way to do it is that you create a random number seed according to the date and time. And so that's what this -1 is telling it to do, is use the date and time to create a unique seed, and then see the random number generator and creates these random numbers. Output format, 0, means the output is ASCII. So you can read it. To save space, people will use binary output, but that's not human readable. You have to have a program read it. Okay, so we can run the heating simulation the same sort of way. This would be the command use all that. You notice that the input file is the end of the minimalization. The restart file at the end of the minimalization. So, yes, so I'm starting from that final configuration, and then I heat it up. So now we can load the results in V&V and see what this did. So that's in the file heat. Now you want to make sure that you load it with the periodic box. Otherwise, it reads in the coordinates incorrectly, and it looks really weird. But uh-oh. Oh. That's because I told it to read the wrong file. So this is the final position in the minimalization. And then I heated it up. It's moving very fast. So I'll slow it down a little bit. That's a little slow. All right. So here, they start moving faster. And I want, and what's shown initially is the particles in what we call the main simulation box. So that was this one right here. But as the simulation's running, these things are also interacting with their periodic images, and that's what's shown over here. And they're all this is replicas of the main simulation box, and I made D&D show it in the X and Y directions, but it's in the Z directions. And it's replicated effectively, infinitely, in every direction. And this is how we go from simulating we approximate an infinite system in the molecular dynamics simulation. Yes?
So like as we're watching this, the molecules that appear to be jumping from one box to the other, are they actually jumping, say, from the top of the one box that's being simulated to the bottom of that box?
Yeah, so it depends. So so you see this benzene, yeah, as it goes up through there, it's coming into the bottom.
it just shows up in our calculation back in the bottom because of the periodic boundary.
Yeah,
Okay.
it's kind of thought of as the same molecule. So there's an important thing to keep in mind about this. So when you think about liquids, or we look at atoms and their motion or molecules and their motion, a lot of times we want to know how their motion is correlated or how their positions are correlated. So when we have these, when you have your benzene that goes, move it up here, there's effectively one down here that's identical. So they are, strictly speaking, exactly correlated. So when you calculate correlations, you calculate positions like how this molecule moves with respect to one down here, you have to be sure that those correlations are only half the box length. Otherwise, you get correlations of the same molecule. And this is unphysical. This doesn't happen in the real world. So this is one of the reasons why you do have to have boxes that aren't really small. You can't do just 2 or 3 molecules in a periodic image and say it's an infinite system. And this can create artifacts in the simulations that don't exist in the real world. But, so you create a box that's big enough. You check things by calculating correlations and make sure the correlations decay to a sort of distance that's not affected by your box size. We'll talk a little bit about how to look into that, but yeah. But any questions about that? No? All right. So as you can see here too, there is a so my benzene fluid here, I have defined a box and heated it up, but the fluid is not filling the box. I don't know at these conditions whether or not it should. But if say I'm interested in it at ambient conditions, what exactly do I do? The next thing I want to do is, so now I've heated it up, and I heat it up not instantly, but a little slowly, and this is just so I can create the initial conditions in a controlled manner. And there's my periodic boundary conditions. But due to the question here, we kind of talked about exactly this. That it's replicated so that these molecules are the same. And so as they move through the box, they move together. All right. So I want to equilibrate it to ambient conditions. So I'm going to equilibrate it now 298 Kelvin in 1 atmosphere. So in the input file, once again, we have all these other parameters. I tell it I'm not minimizing it, I'm running it as continuations. Now I'm going to read in coordinates and velocities. So that's what this ntx equals 5. I'm using Langevin temperature coupling. You need some sort of thermostat because the system's not in equilibrium. So what happens if you just run Newton's equations of motion? There's no temperature in Newton's equations of motion. It just runs at some constant energy, and it probably won't end up at the temperature, and the average pressure will be the pressure that you want. So we need to somehow run the simulation so it ends up at a temperature with a configuration that's consistent with the temperature and the pressure that we're interested in. So, so we're going to run a constant pressure simulation. And the one means we're doing isotropic pressure scaling. All this means is that when you run a constant pressure simulation, it changes your simulation box. So you remember the periodic boundary conditions. You had your center simulation box. So this is the main box. And so the constant pressure simulations, what it'll do is it'll change the size, and it can change the shape of the box. Sometimes that'll be important also, but it'll change the size of the box, and that changes the density and the pressure. So the isotropic means that it changes each side of the box, x, y, and z, by the same amount. Since we have a fluid, that's a good way to do it. Sometimes you may want to try and change different sides or have one side fixed. We're going to use a Monte Carlo barostat, so I'll briefly describe the idea of what that's doing a little later. 1 atmosphere of pressure. I tell them to use the shake algorithm with fixed hydrogen bonds. And the IRAP, I'm telling you not to put the particles back in the box. So this is done to do calculations. So when you run these simulations, like we discussed, as a particle goes out the box, its image comes in the other side. So you can think of it as either just take the particle that's leave the box, and put it here, and keep track of that coordinate. It's essentially the same particle, the same motion. However, when it does that, if you translate it back in, you take your trajectory, and now the particle has jumped from here to here. If you're interested in how it has moved, its dynamics, then you have to figure out whether or not you've moved it back into the box. And that can be difficult if you just have all these lists of positions. Now, but then if you don't keep track of that, and you're curious about the structure in the middle, then you have to somehow find out how to put this particle back in the box when you do a calculation for structure. Because otherwise, you don't know where its image came in. It turns out that it's much easier to put things back in boxes than it is to figure out whether or not it's left a box. So I will show you how to do that. So I always save my configurations unwrapped. Other people don't necessarily do that, and if you're not concerned about dynamics, there's really no reason to do it. But I always save them out. And once again, the output is ASCII. All right, so equilibration. So I started the equilibration run. We'll take a quick look at here in a second. Once again, very similar sort of long line of file names and input. And so I'm restarting it in the end of the heating trajectory. So I heated it up, restarted it, ran this equilibration. And then I created, you can look at the log file and the information file. And then I created 3 files, and there's a Perl script that can create these files. So you just run this Perl script, and it should be, it was last year, it should be on the cluster. So all you have to do is run that Perl script, and give the log file name, and then it'll create these summary files. and they always have these same names. Okay? So let's take a look at one. We can take a look at the simulation real quick. Going to be the most exciting, but so I left them unwrapped. So which means that when you take a look at it now, it initially appears that we have benzene out in the middle of nowhere. That's not really the case, because if I added the periodic images, you can see they are interacting with their periodic images. Now this thing is definitely looking like it's, yeah, especially near the end, it's looking like it's becoming a homogeneous liquid. And that's what we're interested in, the properties of this liquid. Do you know how to add the periodic box to this?
There's not an easy way to do it.
Okay. I don't even know how to do it. I've never done it. Anyhow. But what actually happens here, and we'll look at it when the output file see, is that as this is running, this is our center box, and this box is shrinking also to equilibrium with a specific pressure. So that's why one of the reasons it's so spread out initially, and then you can see it come together to form what looks like a homogeneous liquid. Now when you look at this, you may go, well, okay, I'm done. But let's see a little bit more how we determine whether or not it's equilibrated. Well, hopefully I forgot to ask him. He's got a new plot. He does. So we can plot some of these. Which one do I tell you to plot first? Okay, so we're going to look at the total kinetic energy. So this summary, EK total is the total kinetic energy, and this is the temperature. And then I have to remember, maybe I should write it down, it's 5.9616. And the point is going to be, the temperature is determined from this total kinetic energy. So it's what we call the kinetic temperature. And that is just the average of the mass of the particle and the velocity squared is related to the temperature. This is not the only method to determine temperature in a simulation. There are many things related to temperature, many probability distributions, and any of these can be used to determine a temperature. This is by far the most common, and a lot of times when people talk about temperature in a simulation, this is what they're talking about. So, fortunately, and what was it called? So this is the kinetic temperature. The thermostat is controlling this. So the constant temperature thermostat is controlling it. So kinetic energy is the top, and then this is the actual temperature. This is what we put into the program. You notice it's not constant. And this is good. We call it a constant temperature simulation, but the kinetic energy at a given temperature of a system is not a constant value. It fluctuates around an average value, which is given by the temperature. So this temperature value, since it's related to the kinetic energy, is its average value. Should be the temperature that you put in. So, just as the demonstration, if I plot this, so the temperature yes.
Looks like it's behind.
Oh, it is, isn't it? There it is. Thank you. You can. The points now are overlapping. I don't know how well you can see that, but there's an X and a plus. So all this thing, all the program is doing is using the kinetic energy to get a temperature out of it. It's called the kinetic temperature. So once again, it's not constant, but its average value should be related to the temperature. All right. So next. So we can plot the total energy. We plotted the temperature, and then the volume. Okay. So at the end of that simulation, everything yes. It looked like that it became a homogeneous fluid. But if I look at the total energy, I notice the energy is decreased, right? The energy decreases, and when I'm done, it still looks like it's decreasing. So even though that visually, to the visual inspection, it looked like I had equilibrated, I hadn't. It's not done yet. The full simulation, equilibration simulation, takes so long to, either you don't save it enough and it looks silly. It takes so long to do that you can't, you don't want to watch it. So, what you want to see here for an equilibrated simulation is that this total energy should level off and fluctuate around some sort of average value. It's the average energy. And that hasn't happened yet for that simulation, even though visually it looks fine. And then you can plot the volume. In the simulation box. So this is just the volume of that center simulation box as we ran the simulation. And you notice that, once again, it is just decreasing very rapidly. And when it's equilibrated, when the system is starting to produce configurations consistent with the temperature and the volume that we're interested in, the temperature and the pressure that we're interested in, thermodynamic conditions that we're interested in, this, once again, will start fluctuating around an average value. So it just levels off, fluctuates around an average value. All right, so those are things that when you equilibrate it, you need to look at the total energy or potential energy and the volume and make sure that they're reached something that looks like it's not changing anymore. Once again, they're not constant. You call them, well, yeah, this is a constant pressure simulation. Once again, that doesn't mean the pressure ends up being constant. The pressure will fluctuate, but it fluctuates around the value that you give it. So the volume will fluctuate around some sort of average value, as well as the temperature.
So when you were looking at those plots, it was basically each time step along the x-axis and then whatever volume or
Yeah,
whatever
it's-
on the
It's
y-axis.
we told it to output data every so many steps.
DT there, zero.
Well, DT is the time step for the simulation.
Okay.
That's through the numerical algorithm. So I have to, it's written down here somewhere. So NTWR is how often we save restart files, and then there's, unfortunately, I don't use this program. At some point, I think it's the initial one. Okay.
Yeah.
NTP yes. So this is the one, NTPR is how often we print out the volume and the energy. So then when you run the script, the Perl script, it creates those files that makes it easier to look at, right? Okay. So like I said, that simulation did not equilibrate. So you need more equilibration to actually calculate the quantities that you're interested in. So later on today, or should do this quickly, because the simulations take a little while. But as part of your project this afternoon, create the input file. You can use the last file, the output that's in the folder that I gave you as the input file, right? But create the file to run the simulation. You know, you have the template there. Output information every 1,000 times steps, and then you run the simulation for 1.5 million times steps. And when I did that, it reached equilibrium. So that should be able to equilibrate it. And then you can look at everything and see what the energy looks like and the volume looks like and everything looks like after it's equilibrated. All right? Now, to some extent, this has been a black box. Exactly what goes on underneath it. And I don't have enough time to go through all the details of how these multi-dynamic simulations work. I do want to not make this to be completely confusing about what exactly we're doing. So for the temperature, the thermostat, we use a Langevin equation. And this looks a little, so this is mass 2 times derivatives of the position. What is this? This is mass times acceleration. This is your force, right? So F equals ma. That would just be Newton's law. I didn't have these other two terms. So these other two terms are dot, single derivative of the position, is just u velocity. And this gamma is what we call friction coefficient, because what this means is that as something moves a certain velocity, it slows it down. Right? Well, if we're slowing it down, we get a slight problem because it eventually stops. We don't want it to stop. So what we do is we add random kicks to it. This is what's called Brownian motion. Einstein's very famous for this. And as long as gamma and these are related properly, what it does is it creates a system with the proper temperature, has the proper configurations corresponding to the distribution that you're interested in. And it ends up being a fairly efficient way to equilibrate systems. So I use it frequently. So this gamma, this is gamma ln, this was given in the input script. And this is related to how quickly you damp the velocities. So it needs to be, if you make poor choices, don't damp the velocities very quickly, it will not equilibrate. If you damp them very quickly, then it takes a long time to equilibrate also. So what I gave in the input script is a good value. You actually have a large range of good values, but you do have to be careful. All right, so that's how that thermostat works. There's a lot of details about it I left out, but that's a general idea. The barostat was a Monte Carlo barostat. So I don't know if anyone's heard of Monte Carlo simulations. So what is, so in statistical mechanics, you have certain ensembles, and you want to create systems that are consistent with those ensembles. So you want to have, if you take each volume you have, or each density, in a constant pressure simulation, and you average that, or it should be, and you look at the distribution of that, it should have the proper distribution of volumes that you expect in an NPT ensemble. And so Monte Carlo simulations, and this Monte Carlo barostat, does exactly that. It creates a distribution of volumes consistent with constant pressure ensemble. So what it actually does is it tries to change the volume by a certain amount. Just a random volume change. There's a maximum change. And then it asks itself, is this volume change consistent with this ensemble? And it keeps and rejects the volume changes to make sure that the distribution of volumes are consistent with your ensemble. And this is, you can actually do simulations this way to get average positions of particles, orientations, and everything. It is not, but its time dependence would be incorrect. So if you're interested in how things move, that would not be a good way to do it. But so that's what the Monte Carlo barostat is doing for you.
You have a question?
Yes.
So is it constantly changing that volume
So,
throughout the
no,
entire simulation? Or is it just...
So if you have the barostat, it constantly changes it throughout the simulation. What people will do is use the barostat to find the average volume, and then you can run on the simulation at that volume, right?
It's more so to.
So remember, while it's doing this, it's changing the size of the simulation box. I'm glad you asked this question because I should have brought up this point. When it does this, it rescales all the positions of all the particles inside the box. So, there's nothing in Newton's equations of motion of rescaling particle positions as pressure changes. That's not there. So this is an unphysical thing.
So they're never gonna
But
use-
it does create a simulation at the conditions that you want. So the configuration at the conditions that you're interested in. So if you look at the dynamics again, if you're interested in how the particles move, this changing of the volume does change that dynamics. Most people believe that it averages out once you're in equilibrium, but it's something that you need to know and keep in mind. So after we equilibrated, you have, we start answering our questions. We start running production runs. Then we produce configurations that's useful for our desired calculations. You can do two things when you do this. You can, during the simulation, you can have it calculate what you're interested in and just print out the answer when it's done. Or you can save a representative number of configurations and then use those configurations and velocities later to calculate averages. And I'll mention that in a little bit. And so I will run constant energy. I'll show you an example where we run constant energy. And running constant energy now, we call it NVE. So now I'm going to fix the volume of the box, fix the energy. So the total energy is fixed. Remember, that means the kinetic energy will fluctuate. The temperature fluctuates. But if we have properly equilibrated our simulation, the kinetic temperature just fluctuates around the average value of the temperature that we just equilibrated it to. Okay. The one thing, this is becoming more, when I first started doing this wasn't a concern. Becoming more and more of a concern. Very long, your computer is not perfect. There are round off errors. So simulations get very long, billions of time steps. Your energies and everything will drift, and there's nothing you can do about it. Well, you can make the computer precision as accurate as you can, as you want, but then that always slows it down. So to deal with that, a lot of times people will use a very mild thermostat, something that doesn't change the dynamics too much, but still keeps the energy and temperature around the same value. But that's not going to be a problem for us. We're not going to worry about that. So after we've saved these things, we want to use the positions and velocity to calculate the averages of interest. So how do we do this? Well, in statistical mechanics, the idea is that you have a distribution of positions given by whatever Boltzmann distribution most of the time, and you average whatever you're interested in. You average over that distribution as a function of, positions, or if you're interested in is related to velocities, and the momentum. So just thinking, what we do is we actually average over all your saved configurations of the positions with the momentum. And this should be equal to, this time average that we're doing in simulations should be equal to the ensemble average that you take in physical mechanics. If this is, we say if the systems are ergodic, they should be equal. And most of the time they are, but and Martin will talk about this a little bit. What can be difficult is it can take the system a long time to go from, say, one state to another one, just running a molecular dynamics simulation. And so there are tricks to get around that, but he'll be talking about that later in the week. For our benzene liquid, fortunately, that's not a problem. We can also, so this is just a simple average quantity. Say an example here is that this is just the energy. So the kinetic energy is just a function of the momentum. You just average the kinetic energy over all these saved configurations. Or you can have potential energy, which is just a function of the positions. You can average the potential energy over all the configurations. We might be interested in other things. For example, and I'll talk about this example, if I'm benzene molecule here, I'll be interested in what is the probability of me finding a benzene molecule sitting right there, so far away from me. And that would be an example of a static correlation function. But these are two functions, possibly functions of position or momentum. And yes, this is the same as if we take averages of these correlation functions at the same time. So you just calculate the functions of these two functions at the same time to calculate the averages. You can also be interested in time correlation functions. And this, once again, a formal definition of this, but now see that we're interested in two things at two different times. An example, simple example of this is if I'm benzene molecule here, and then at a later time, I want to ask, how far on average do I move away from this position? We certainly don't, if we look at the square of that. So we look at the mean square displacement. So these are formal definitions, which I always find are not very useful until I do something concrete. So one example here for equal time correlation function, what I was talking about is the apparent correlation function, which is, this is the definition of it, and it's related to what I was saying. If I'm a benzene molecule, what is the probability of finding another one a certain distance away from me? This is the most common way to characterize the structure of liquids. Okay, so you will be calculating G of R. And when I was told about this, have you guys done probability distributions, calculated histograms? You guys haven't done it. All right, so this is why I wanted you guys to have the slides too, because this describes it how to do it. So what you'll do is you'll divide positions, and in a few slides I'll tell you how to do that too, into intervals. And then we're going to find the distance between two different particles. We'll be using the center of the benzene. So these two different points can be the atoms, center of mass, geometric center, etc. And we'll create a histogram. So to create a histogram of the points, you Oh, you take the distance between the particles divided by whatever bin size you have, and you'll get a number. So take the integer, whatever this division is, and you get a number, 1, 2, 3, 4, 5, maybe 0. And then you add 1 to these histogram bins for every time you get that. You do that for each one of your configurations. You divide it by this normalization, and you get G of R. This is normalized, so it goes for 1 for large R. 1 is actually its ideal gas value. And this is why we have this phi down here. It's if some points were just randomly distributed in space. There are no overlaps of particles. You just randomly distributed it. This is what you would get for a bin of a specific size. So this interval, 4 pi rho, integral from 0 to r, d of r prime dr prime. That's just the number of points, which could be your atoms, your molecules, the center of the molecules, whatever, found around the origin of G of R. So this is, if you do this for benzene, the center of the benzene, this is just asking, this interval tells you how many benzene molecules are found in a distance r from center 1 benzene. All right. So, we had periodic boundary conditions. So this complicates things a little bit. So one, I said I always do not wrap them back in, save everything what we call unwrapped. So now when we calculate G of R, if one particle has gone 3 periodic images over, I need to know that its image particle is back in this box, how its position is related to the other one. It turns out this is pretty easy to do. So if you have particle I and j, you find the distance between the particles, and you just have one, say, that's in your box, and one way over in this other box. You just find that distance, even though this is not the distance you're going to be using. But the actual distance between the one that's in the particle that's in the box and the other one in the box is the length of the box times this nearest integer of the distance you calculated divided by the length of the box. So that's just an elevated distance away from the particles. If you want to put the particle in the box, you can do this. Delta is just position of the particle. It's the same thing. That'll translate the particle all the way back in the box. So let's do the same for the y and z directions. The nearest int is the nearest integer function in a Python. You can implement it this way. So that's how you deal with the periodic boundary conditions to calculate G of R. Like I said, it's much easier to do this than to figure out every time that it leaves a box. All right, so an example, a very typical example of a time correlation function is what we call velocity autocorrelation function. And here we're summing over all of our particles of the dot product of the velocity at time equals 0 and the velocity at some later time. So this at t equals 0 is related to our temperature. And this is just the square of the velocities. And as time goes on, this eventually becomes uncorrelated. Another one, which is actually related to here, is the mean square displacement. So this is the average, it's 1 over number of particles, and this is the sum of the square of the displacement of a particle. So the position of the particle at time t minus the position at 0 and that squared. And then what the average means is that for every time origin that I do this calculation, I average over time origins to do this calculation. So you have time 0 in your simulation, but this is a time difference. Then you have t at a later time. Then you can take a different time origin. That's your next save configuration. And then the time is then the next one on the save. So the same time difference, which you have to average over your time origins, save configurations. Another example is an energy correlation function. That's just an example of a time correlation function you can calculate. So this is, since you're going to be doing this calculation, I wanted you to have a slide that shows you a little bit more about calculating the mean square displacement. All right. So like I said, you sum through the time origins. You get these. So every saved configuration, you can sum through the origins of time. And this is the saved configuration of time t later. So here we're averaging over the number of time origins for this time t. So that's why I have this t. Then you also sum over the number of particles. Or we'll be doing the benzene centers. Because these are vectors, you actually break it out in the square dot product. You break it out into components of x, y, and z. All right. And here's here's the results of one of the calculations. I don't remember if this was an equilibrated one or not, but for long times, the mean square displacement becomes linear in liquids. So this is why this just looks like a straight line. You notice out here, there's some wiggle, some noise. You know, that occurs because when we do the average over the time origins, you have only so many saved configurations, and at the late times, this time difference, you don't have that many intervals of that time difference. So the later times, the noise gets larger. So that's why we have the wiggles at the end, but it's pretty straight. The diffusion coefficient, especially by definition, the diffusion coefficient related to the mean square displacement at long times, and so we'll calculate that later too. All right. So how do we do these calculations? Many different ways to do it. But here I'm going to show you some examples of using the MD analysis toolkit, which is a Python tool to read, write, and analyze molecular dynamics trajectories. So first you need to have your trajectory. You need to know what you want to calculate. And you need to know how you're going to do the calculation. So the basics of this is to do the analysis, you want to, and this should be, I was told that you guys have access to this. All right, okay. a lot of the tools, you'll use NumPy, so you want to put that in the analysis. You put the math and the scientific analysis. You start off by creating a universe. Okay? So you have your universe. You name it. This is your variable in Python. You create a universe topology file. You remember that I always loaded in this PRM TOP file. So this is your topology file. So, and then that once again gives it gives Python information about your system. And then you can load in the trajectory file. You can also make selections of atoms. There's so many various ways to do this that I'm not going to go through any examples here, but you'll be using BMD more in the next couple of days. And the atom selection is very similar to the atom selection BMD commands. Keep that in mind, and online you can look through how to make those selections. So we want to loop through trajectories, obtain coordinates and whatever needed information to do our calculation, and do the calculation. So here's an example of how to do this. For TS, for each time step in our trajectory, universe trajectory, I say that the coordinates equals time step positions at that time step. The box, so I can get the dimensions in the box, of the simulation box, center box, of the time step. And you'll need those dimensions to do calculations. So this is a multidimensional array, and okay, so I is a particle, and J corresponds to the X, Y, and Z position. So this would be the first particle in the simulation, or the carbons, possibly, in your benzene. And then J, if you set J equal to 0, that's the X position. J equal to 1, that's the Y position. And J equals 2 is the Z position. And so this box of J, once again, 0, 1, and 2, is the length of the simulation box in that direction, X, Y, and Z. All right. So here's a full example that all it does is write out the coordinates of the center of your first benzene molecule in the simulation. So let's go through quickly what this does. And so, for you, you'll have a 200 here. But this is your parameter file. So I create the universe and read in my trajectory file. Now, then I select all the atoms. Makes it easy enough. That's what all it is. I can print out that you have access to many things. But you can print out the number of atoms and the directory. Just print out the number of frames. So when you do your simulations, it's nice to know the number of frames and the number of atoms. When you do the calculation, then. And then I'm just going to print it out to this test box. that I opened for writing. So get the same coordinates, the box, find the centers, equal to 0. So then I'm looping over for I in range to 12, which is 12 atoms of my first benzene molecule. And so the center here, I'm averaging all the centers, 5 by 12, that's how many particles we have, and then I write out the output in the XYZ position. So that's just an example of how to get the information you need to do the calculations for the analysis. So I think we're about done. So for this afternoon, for the homework, I'd like you to equilibrate the benzene simulation. I mean, I've already memorized it. You can start it. And run a constant energy run of 300,000 steps. So, like I said, I think it took about 1.5 million time steps to equilibrate it. This does take a little while, so you may want to set that up and run it before lunch. It didn't take terribly long for me, but I don't remember. It's like an hour, 45 minutes or an hour. And then run a constant energy run. And then compute the pair correlation function for the geometric center of the benzene molecules. You can, like I say, calculate these pair correlation functions for individual atoms, lots of things, but the geometric center gives you an idea of what these pair correlation functions look like for fluids. So, and then compute the mean square displacement for the geometric center. And then from that, you can get the diffusion coefficient. I had a slide earlier showing you how to do that. And I think that was it. I could be wrong. No, that was it. So are there any questions? I'm sure there will be later on in the day. My office is C127. You can feel free to come and talk to me. I'm kind of have to go around, and several people who share that room. Tony's one of them, right? And I'm kind of tucked around the corner. So if there's someone in there, you can ask them where to find me. Surrounded by computers. All right.
So is there like you said it takes an hour, and let's say you set something up and it started to take considerably longer, so you figured, oh, I probably screwed something up. Is there a way to kill your job? Should you know that?
So it depends on the operating system how to kill the job.
So you're talking about in Slurm?
So in Slurm, I don't know how to do it.
In Slurm, you use the S-cancel command.
Right?
So there'll be a job ID associated with every job. You do SID, or S-cancel that ID.
Okay.
If you're running it interactively, if you just run the command and you're waiting for the prompt to come back, you can just do Control-C, and that'll kill whatever you're doing.
And somewhere here, if you go through here, there's a flag telling you how often you're printing out restart files. So if you kill it, you can always
Grab
you can use the restart file to restart it, and so you're not starting from the beginning again.
It just occurs to me that one could set 9 or 10 flags and then regret
Oh yeah.
decision and decide not to put computational resources.
Yes. Yes.
So one of the files that Amber will produce is probably called an MD info file, unless you change the name of it. I didn't notice. But that'll tell you how much longer the simulation has.
Okay.
And so you can check there to see if it seems like things are going okay.
Yeah. Unfortunately, I'm not an Amber expert. talk to Martin's group a little bit more about Amber. Most of my research, I have to write the code myself, so I don't know too much about a lot of these packaged programs.
Are we supposed to run Amber in the Lust reps type directory, or is the program available everywhere? I guess I
You
should.
should run it from mustard, that's the Scratch space.
Okay.
Yeah.
Because then I feel like that would be a really bad idea to not put it on the scheduling.
Oh, yeah, you actually.
Yeah, you put it on the schedule. Yes. All right, we're done.
Okay, great.
How do I stop this?